might be different from some of your other teachers is the very first thing I'll give you in the unit is the outcomes, just so you know what we need to learn. And I'm left brain, so I'm a highlighter. And I'm just going to help you identify the key words. So the first thing we're going to talk about today are what are called translations, which you actually did way back in grade 9, and you did them in grade 11. You just didn't know it. Then we're going to go on to what's called reflections. Again, you did those in grade 9. It's not new. Third thing is something called stretches and compressions. Then we're going to do a combination of all three of those. Then we're going to learn what's called inverse functions. And then we're going to go into two things on sinusoidal functions. Sounds so fancy. Sinusoidal functions. So we'll do transformations of them, and then we'll do applications of them. Okay, so really there's 5 key things in the unit. The translations we'll do today, the reflections, stretches, compressions, inverse functions, and then these things called sinusoidal functions. Okay, I know some of you, it's been a while since you've done grade 11 math. So let's just put a little bit of this back in your head. Vertex of y equal to x squared. Vertex of y equal to x squared. Anyone remember the word vertex? Yes, that's a start. Vertex is you take the number in brackets, you change the sign, that's the x-coordinate. You take the number outside the brackets, leave it alone, that's the y-coordinate. Okay? That's a big summary of what we did in over 3 classes in grade 11. Is there a number in brackets? No, so that means the x-coordinate is 0. Is there a number at the end all by itself? No, so the y-coordinate is also 0. So we know that is what's called the base parabola. Base parabola vertex is 0, 0. What's the vertex of x squared plus 4? What's the vertex of x squared plus 4? Some people are already mouthing it. 0, comma, 4. What's the vertex of x squared minus 2? 0, negative 2. So we didn't really talk about these in terms of transformations, but that's what they are. Transformation just means a change. And what we've done is we've changed the graph by adding that number. What did we do to the picture if it was at 0, 0 and now it's at 0, 4? What did we do to it? Yeah. Yeah, we moved it up. And what did we do to it if it's at 0 minus 2? We dropped it down to. Did we change the shape of it? So did it get wider? And this is back from last year. No. Did we change the direction? Did we flip it over? No. So we call this a vertical translation. It's called a vertical translation. The word translation just means movement. So we have physically moved it up either vertically or back down vertically. Okay, vertex of, now I'm going to stick a number in the brackets, x minus 5 squared. Write down the vertex of x minus 5 squared. Write down the vertex of x minus 5 squared. Vertex is 5, 0. Whoa, what happened to that negative 5? What happened to that negative 5? Why did it suddenly turn positive? Well, that was the thing with parabolas that we always talked about. The thing in the brackets changed sign, and I really didn't tell you why last year. I'm going to tell you why in a couple of days. For now, you just need to know if it's inside brackets, we end up changing the sign. Write down the vertex of x plus 7 squared. X plus 7 squared. Vertex you should have down is negative 7, 0. Again, these are called transformations. Anyone want to guess, just from some logic, what they might be called? Horizontal translations. So vertical translation is when we move it up or down, just depending on the number. And our horizontal is when we move it left or right. Okay, so nothing new. We didn't add anything that we didn't talk about last year. This is just what we kind of started with parabolas, and then we started talking about flipping them and stretching them. But we're just going to stick to the horizontal and vertical movements. So these transformations are called translations. And they can be applied to any function, not just quadratics. And that's where we're going with this. We're going to take what you learned about quadratics, and we're going to apply it to all kinds of different graphs. We're going to look at what's called a cubic function, which sounds cooler than it is. We're going to look at square root functions. We're going to look at absolute value functions that we ended off last year. We're taking exactly what you know about parabolas, and we're just applying it to other functions. That's what this unit is about. We're going to take where we change the width of a parabola and do that with other functions. We're going to take where we change the direction of a parabola and do that with other functions. That's what this unit is about, taking everything you know about quadratics and doing it to a whole bunch of other functions. Stand up. Oh my God. I also like to grab red pen for important stuff, so I tend to do stuff in boxes in red because, again, that's how my brain works. A vertical translation in general looks like this. F of x plus some kind of variable. I'm going to call it a. Why a? I don't know because I needed a variable. If a is positive, what? I just said a word and then I use symbols. What's going on? Well, if you don't know by now, mathematicians, words actually scare us. We like using symbols because it's shorter, it's more concise, plus any language can understand it. How does this mean positive? Because it means it's greater than 0, so it's 1 all the way up to infinity. If a is positive, that is a vertical translation up. Now, if you're a wordy person, you might want to put the word up if the arrow doesn't make sense to your brain. If a is less than 0, anyone want to guess? It is down. What is this f of x stuff? So you've seen that in grade 10, you saw it a lot in grade 11. What the heck is f of x? It just means a function. It might be a quadratic, but it might be something else. So this is just general notation for when you take any function and you add a number, this is what it's going to do. The horizontal is when you take the a, but I'm going to call it a different letter so we don't get confused, and I'm going to put it in brackets. So we call that f of x plus b. I added it inside the brackets as opposed to outside the brackets. Let's talk about if b is positive. And this is the one that doesn't really make sense yet. You just memorized it with parabolas. If it's positive, it feels like it should go to the right, but it actually ends up going to the left. If b is a positive value, it ends up going to the left. If b is less than 0, let's see if I got the smart class. It goes to the right. Look at all that stuff I wrote, and I didn't really use any words. All I used is symbols. That's why mathematicians love symbols. How to tell the difference is this is outside brackets. Outside brackets is always going to be a vertical translation. It's an up and down movement. Conversely, horizontal is when the number is inside brackets. Let's look at example number 1. And I actually want you to cross out this part because I ended up putting up in a cubic after. All we're going to do for this one is just describe the transformations. We're not going to get to drawing them yet. I don't want to scare you. We're just going to describe them. So take a look at our very first function, which is letter A. It looks like a parabola. What's the only difference? I have put in an exponent of 3 instead of an exponent of 2. That is called a cubic function. Cubic, C-U-B-I-C, cubic function. I'll show you in a second what they look like, but just because I changed the exponent is really not changing anything. What we want to do is describe these transformations. I'm going to go left to right, so I'm going to look at the 2 first. If it is inside brackets, it means it's horizontal. Now you can write out horizontal translation. Again, math teachers, words scare us. We call it an HT for obvious reasons. So if you write down HT, I'm going to understand you mean horizontal translation. If you want to write it out in words, you can write it out in words. But that's not enough to describe a transformation. You need to actually tell me what it is and how it moves the graph. So the first piece is naming it, which is an HT. Now talk about the movement. Because it's a 2, it's going to be 2 units. What direction? Left, because the number is positive. Here's how we write that when we're scared of words. 2 to the left. If you want to put that in words, that is a-okay. If your brain is a word brain, that's fine. That is describe the transformation. It's a horizontal translation, 2 units to the left. Now I'm going to grab the -5. Because the -5 is outside the brackets, that tells us it is a vertical translation. Because it's, negative number, it is 5 units down. I have now fully answered question A, and I didn't use a single word. Describe the transformations, there they are. The point of this is describe tends to invoke paragraphs. It tends to make you think of words. It doesn't have to be. Describe mathematically does not necessarily mean words. It could. If you wanted to describe it in words, you could, but you don't have to. We also have symbols to describe stuff. Look at scary letter B. What the heck is this? Well, it's not quadratic. How do I know it's not quadratic? Doesn't have an exponent of 2. You now know it's not cubic, because a cubic has to have an exponent of 3. What the heck is this? It's a square root. We call this either a radical function or a square root function, and you would have seen these in the last unit of grade 11. Square root function or a radical function. Nothing's going to change just because that root is there. We're going to take the number inside brackets first. If it's inside brackets, it is horizontal translation. 3 units to the right, because the number is negative. The -5 is outside the brackets, so we assume it is a vertical translation. 5 units down. I'm going to say this all year. Show me your thumb. This means you're going to put your thumb up in the air high so I can see it. If you put it down here, I can't see it. And if it's really high, nobody can see your thumb. And you're going to say, I get this as a thumbs up. I kind of get this as a thumbs to the side. I don't get this at all as thumbs down. And you can be anywhere in between. So show me your thumb so far. Where are you on this translation stuff? Where are you in describing? You got to put it really high because I can't see at the back. Perfect. Okay, second thing we're going to do is a whole bunch of words. Okay. This is a teeny tiny little word problem. We're going to do really long word problems later. Who hates word problems? Yep, most left-brained people we do because there are too many words. Here's how I'm going to do all word problems. This is a 2-step approach. The first thing I'm going to say to you all year is read to read. What that means is I don't want you to think about this. I just want you to read this like it's a sentence in a book, a really boring book. But bear with me, it's just a sentence in a book. If you're already starting to think about the math behind it and what's going on and what do I need to do, you're not really getting the context of the problem. I just want you to read it and put the general idea in your head. Then I'm going to say read to understand. Read to understand is where we pick out what are the key words. And if you're left-brained, you're going to want to highlight with me. We pick out the key words and we avoid what we don't need to know. So read to read. Don't overthink this. Just read it like it's a sentence in a book. All you might have gotten on the read to read is it's something about translations, something about transformations, and that's okay. All you're doing is you're putting the context in your head, and what your brain is already doing without you knowing it is pulling out everything it knows about translations. So once you've read to read, it's already trying to activate what's everything I know about this without you telling it to. Second step is now let's read to understand. So in the first sentence, what do I really need to know? Actually, I don't care it's a graph. I just care about the function. If your brain wanted graph, you can highlight that. Translated is going to be important because that's what we're talking about today is what's called translations. What else do I need to know? 3 up, 2 down, or 2 to the left, sorry, 2 to the left. The second sentence, I like to find what is the word that they're asking you what to do. So is it describe, is it solve, is it determine, is it find? What is the action word they're asking you to do? Write. What are they asking you to write? Equation. Here's how you'll know if you've picked out all the keywords, is I want you to close your eyes. And if I can see the whites, then they're not closed, so close your eyes. I'm going to read you out the words we highlighted, and you're going to tell me if we have enough to be able to do the question. Y equals x cubed, translated, 3 up, 2 left, right, equation. Okay, open your eyes. Do you think we have all the keywords? Okay. If you start doing this on simple word problems like this, when we get to the big ones that are like paragraphs long, they're going to become a lot less scary. When you come up and ask for help, you're like, I don't get this question. The first thing I'm going to ask is, what are the keywords? So you might want to do that before you come up, because I'm going to ask you to do it anyway. Okay, that's how I'll do word problems all year. Read to understand. Read to read is just get the context. Read to understand now is start to pick out the keywords. They're asking us for an equation. What they're asking us to do is take this guy and write it with the translations. So I know I'm going to keep the y. I know I'm going to have an x in there somewhere, and I know I have to have a cubed. We just need to fit those numbers now where they need to go. If it is up, is that horizontal or is that vertical? That is a vertical translation. Does the number go inside brackets or outside brackets? Outside, so I'm going to add it on to the end. How did I know it was +3 and not -3? Because it's up, and up means the number has to be positive. Left means horizontal or vertical? Horizontal. Does that go inside brackets or outside brackets? Inside. So now I got to add some brackets in here. If the number is to the left, what's going to happen inside the brackets? It's going to be +2. That's all the question has asked you to do. It's the identical question from last year. If I had said to you, a parabola y equals x squared has a new vertex of -2, 3. Write the new equation. Same thing, we're just now applying it to what kind of function? Cubic, a cubic function. How are we feeling so far? Okay, now we're going to get to the actual graphing part. You must have a red pen for this unit. So if you don't have one, where could you find one? Bucket here, over here, right? Red flowers, red pen. So if you need one, grab one now. Right now it's going to seem silly because we're only going to have a couple graphs on our set of axes. When we get into combinations of transformations, we might be doing 6, 7 different graphs on the same set of axes. To non-visual people, this is really confusing. More importantly, if you've made a mistake somewhere early on in the question, I can't find it when there's that many graphs. I don't know which is the last one, what's going on. So with all of these transformations, the very last graph must be in red, and that is simply so that I can find it when I'm marking your questions. The very last graph that we do is always going to be in red, because then when I look at it, it pops out for me. Again, if you've got a whole bunch of graphs and you've made a mistake, it's almost impossible for me to try to figure out which one is what and what's going on. Red means red in my classroom. Because I'm left brain, we're very precise people. Red does not mean orange. It doesn't mean blue. It doesn't mean black. It doesn't mean blue with a little note. This is supposed to be red. Red means red, okay? So make sure you've grabbed a red pen at the beginning of the class or you have a red pen with you. Okay, let's do our very first graph. I'm a pencil person when I start graphing because if I make a mistake, it bothers me to have an incorrect pen graph. It's left brain, we can't help it. If you're a pen person, use pen, but I'm going to start by using pencil. The very first thing you do when you look at a question like this is what you want to do is take away the numbers, and we want to know what is the base graph. What does this graph look like if I take away the transformation? So I'm going to ignore this 3 for a second, take it out of there. If I ignore the 3, we're going to say, actually I'm going to do this in pen so you can see it. We're going to say the base graph is y equals the absolute value of x. You graphed the absolute value of x last year in grade 11, but let's just review. We're going to do the first one with the table of values just to put back in your head what it looks like. I'm going to pick some x values. We typically pick -2, -1, 0, 1, and 2. Doesn't have to be those values. You can pick any x you want. We just pick ones on each side of the origin. What's an absolute value function? What does it do to a number? Keeps it positive. Why? Oh, the silence. Kind of. What the absolute value of a function represents is the number, the distance on a number line from 0 to that number. So when they say absolute value of -3, for example, they're asking you is how many units are there between 0 and -3? How many units between 0 and -3? 3. And we can't have a negative distance. That's why the absolute value takes away the negative. If a question said absolute value of -9, it's asking you how many units between 0 and -9. How many units between 0 and -9? 9. That's why it turns positive. So the absolute value of -2, it's asking how many units between 0 and -2? 2. Absolute value of -1. Hello!
Is Senate supposed to be here?
No, every second day. Yes.
Sorry to interrupt you. I just had a major moment in our chat moment.
No, it's all good. Absolute value of -1? 1. Absolute value of 0, how many units between 0 and 0? Big fat 0. Absolute value of 1. And absolute value of 2. Is that kind of coming back? Okay, so let's just graph these points. So -2 and +2. -1, +1, 0, 0, 1, 1, and 2, 2. And you remember the shape of an absolute value graph? Yeah, we call it the V. So parabolas are U's, these are V's. When you meet quartics, they're W's. Don't want to spoil the fun. Now, what do you notice that I used there that Abby's coming up to grab because she wants to use one too? Yeah, we are not barbarians in pre-cal. We use rulers to draw lines. If you give me a nasty squiggly line, I'm giving it a 0 because that's just yucky. There's always rulers up there, so if you need one, just grab it. If you ever don't have, use the side of your phone, use the side of your calculator, use the side of a book, but no squiggly, nasty lines, right brain people. Questions so far with how I drew the base graph? This should kind of be in your head from last year. I don't expect you remembered all of it, but it should look familiar. Now I'm going to go back to the question and add my transformations. This is a 3 and it's inside brackets. If it's inside the brackets, what do I know about it? It's horizontal. Because I am adding it, it's a translation. We're going to get into what happens when you multiply and divide later on. That's why I said that. It is inside brackets, so it's horizontal. I am adding it, so it is what's called a translation. Now I'm going to finish describing it. This is 3 units to the left. Why is it to the left? Because the number is positive. Positive goes to the left. I'm going to show you 2 different ways to do this, and you're going to like one of them better. Pick whichever one you want. I'm going to do the more visual way first. I'm grabbing red pen because my last graph needs to be in red, and this is our last graph because we only have one transformation in the question. All I am going to do is I'm going to look at these points, and I'm going to take every single one of them and move it 3 units to the left. So if you can count, you can do this. This is like kindergarten. I'm going to take this first point, which was at -2, 2, and all I'm going to do is count 1, 2, 3 spaces to the left. I didn't move it up and down, I just moved it to the left. Then I'm going to take my -1, 1 and go 1, 2, 3 and put a dot there. Then I'm going to take my 0, 0, 1, 2, 3, put a dot there. My 1, 1, 1, 2, 3, put a dot there. And my 2, 2, 1, 2, 3, put a dot there. Join the dots. And there's your first transformation of an absolute value. Again, I know it's silly to use red when there's only 2 graphs, but we want to get in the habit because, again, when you have 6 or 7, it's impossible for me to see which is your last graph. Now, when you finish a question, you want to look away, like physically look away from your graph, And then look back and say, did I do what I said I was going to do? Did I pick up this graph and move it 3 units to the left? Okay, so always look away, because sometimes when you look at something, it's too close in your brain. Look back. Did you pick it up and did you move it? That is one way to do this question. I'm going to show you a second way to do this question you might like better. What I'm going to do is I'm going to go back to my table of values, and I'm just going to play with these numbers. And what I'm going to do to each of them is subtract 3, because it's 2 units to the left. I completely lied. We're going to the x-coordinates because it's horizontal. Yes, to the x-coordinates. If I take negative 2 and I subtract 3, what number do I get? Negative 5. And if I take negative 1 and I subtract 3, what do I get? Negative 4. And if I take 0 and subtract 3, I get negative 3. If I take 1 and subtract 3, I get negative 2. And 2 subtract 3, negative 1. And then what you can do is just plot the new coordinates. So go to negative 5, 2. There should already be a dot there. Go to negative 4, 1. There should already be a dot there. Go to negative 3, 0. There should already be a dot there, etc., etc. So you can work right off the graph, or you can work off a table of values. It's completely up to you and how your brain works. Thumbs, I'm getting this, kind of getting this, not getting this, anywhere in between. Good. Oh, our first cubic. I love cubic functions. The very first thing you need to know with all of the questions in this unit is the y has to be isolated. Transformations only work the way I've described if the y is all by itself. So you might want to write a note in red pen, step 1 is always isolate y. Y is a W-Y-H, W-H-Y. Why? Why? Why do we need to isolate this? Well, right now it looks like positive 1, which looks like we're going to move it up. But when we move it to this side, what's going to happen? Right, so we'll try to trick you by putting these transformations on the other side. Step number 1 is to isolate the y and get rid of that 1 and move it all to the right-hand side. Step number 2, and I'm doing steps for this one for right or left brain people, we like steps. Step number 2 is going to be draw the base graph. That means take out the numbers and what is the basic graph that this is. So if I take out the 2 and I take out the negative 1, what is the base graph for this question? Y equals take out the negative 2, take out the negative 1, what's left? X cubed. That's our base graph for this before any kind of transformations. Okay, first time probably seeing a cubic. Let's start with a little table of values. Eventually you'll just know what a cubic looks like, just like you know what a parabola looks like. Negative 2, negative 1, 0, 1, 2. Again, do you need to use those x's? No, it's just kind of typical values we choose. Okay, so if I put in negative 2 cubed, so negative 2 times negative 2 times negative 2. Two times 2 times 2, 8, negative 8. Negative 1 cubed, negative 1 times negative 1 times negative 1, negative 1. 0 cubed, 1 cubed, and 2 cubed. Again, I like to do in pencil because I hate when I make a mistake. It's not my fault, I'm left-brained. Okay, let's look at our first cubic. Negative 2, way down here at negative 8. Negative 1, negative 1. The origin at 0. 1, 1. And 2, and way up here at 8. What the heck kind of graph is this? Here's what it looks like. It's like a snake. Parabola is the U, absolute value is the V, cubics are the snakes. Is that not kind of a fun graph? A little bit. Step number 3, describe the transformations. Describe the transformations. The -2 here is inside brackets. Inside means it is horizontal. It's a subtraction, so that's a translation. It is 2 units to the right. That is describing the transformation. It's a horizontal translation, 2 units to the right. Grabbing our -1, it is outside brackets, so that is a vertical. It is an addition or subtraction, which means it's a translation, and it is 1 unit down. This time I'm going to do that method with the table of value first. If you just want to draw off the graph, wait and I'll get there. What this means is that we are adding 2 to the x because we're going to the right, and we are subtracting 1 from the y because we are going down. So if I take -2 and add 2, I get 0. If I take -1 and add 2, we get 1. If I take 0 and add 2, 1 plus 2, and 2 plus 2. -8 minus 1 is going to go to -9. -1 subtract 1, -2. 0 minus 1, -1. 1 minus 1, 0. 8 minus 1, 7. So if you like that method, you take these new coordinates and you graph it. For the people that just want to work off the graph, I'm going to grab my red pen because this is going to be my last graph, and all I'm going to do is count. I'm going to go from the left to the right, so I'm going to start with this point that's way down here. And all I'm going to do is pick it up and move it 2 to the right and 1 down. 1, 2, 1 down. Then I'm going to my -1, 2 over, 1 down. Now I'm at the origin, 2 to the right, 1 down. 1, 1, 2 to the right, 1 down. Way up here, 2 to the right, 1 down. And then I join them in that snake eve pattern. It does not connect the dots that you're using straight lines. It has curve and bend to it. Use whatever method works for you. If you like to count right off the graph, count off the graph. If you like to use the coordinates, use the coordinates. You don't have to use one over the other. Step number 4 that we just did was graph the transformations. How are we doing so far? Good. So we did an absolute value, we did a cubic, now we're going to look at the square root. Steps aren't going to change just because it's a different function. What is always step number 1? Isolate y. So what do I need to do with this -2? Add it to the other side. Strip away the numbers. The base graph is going to be y equals the square root of x. Again, until you know what this looks like, there's nothing wrong with using a table of values. Now we need to be a little bit smarter with our x values, and I'm not going to do -1, -2, 0, 1, 2. And the reason is, if I put -2 in here, can you do the square root of -2? No, doesn't exist. Can we do the square root of -1? Doesn't exist. Can I use 0? Can I do a square root of 0? Yep, the square root of 0 is 0. If I stick a 1 in here, are we okay? Do we have a square root of 1? Yes. Square root of 1 is 1. 2, not a good number, because the square root of 2 is a nasty decimal, and I don't want to have to work with that. So I could get my calculator, I could get the decimal, I'm just lazy. 3, no, 4. Okay, we like 4. Why do we like 4? Perfect square, so the square root of 4 is 2. Let's do one more number. What's the next best number to choose? 9. Square root of 9, 3. Again, you don't have to pick these x values. I'm just picking ones that are nice for us to calculate. Okay, let's look at your first square root graph. This is so exciting. 0, 0, 1, 1, 4, 2, and 9, 3. Now keep in mind, mathematicians are typically not creative people and we're really obvious. What do you think we call it? So parabolas was the U, absolute value was the V, cubics was the snake. It's a swoosh. Of course, hello, it's a swoosh. It's a swoosh to the right. Because later we're going to have swoosh to the left. It's a swoosh. There's your first square root graph. Jordan's like, Told you, we're not creative people. We are not. We're very obvious. Step number 2 is draw the base graph. Check. 2 steps to go. What's step number 3? Identify. Here's where mathematicians are really, really lazy people. There are actually supposed to be brackets in this question. We just tend not to draw it with a square root because we know it's that whole x minus 4 that's under the square root. But mathematically, there should be brackets here. So you need to imply them in order to understand which is horizontal and which is vertical. So typically with a stair root, we tend not to do them, but mathematically, they should be there. So knowing that 4 is what kind of translation? Horizontal translation because it's inside the brackets that we don't really write. Because it's inside the brackets, it is 4 units to the left. The plus 2 that I put there, it is outside any kind of brackets or outside the square root all by itself off to the side. So that makes it a vertical translation. 2 units up. If you like working with the coordinates, it means you are subtracting 4 from x because you're going to the left, and you're adding 2 to y because you're going to the right. Okay, so if you want to do that, I'm just going to give you a minute to figure out what those new coordinates are. If you're working with coordinates, great, you keep going. I'm going to go with people who want to work with the graph, and I'm going to start at 0, 0, and I'm counting 4 to the left and 2 down. So 1, 2, 3, 4, 1, 2. 2 up, crap. Other left brains will know that that really, really bothers me. Now I just want to burn the whole booklet and start over. Yeah, we're whiteout and eraser people. Don't make fun of us. The next point, 1, 2, 3, 4, 1, 2. And the next point, 1, 2, 3, 4, 1, 2. And the last point, 1, 2, 3, 4, 1, 2. So even if you did the coordinates, you should have the same points at the end. Look away. Look back. Did you pick this up and did you move the graph 4 to the left and 2 up? Now, here's a common mistake that someone's going to do with a square root graph. As you'll notice, this side does not have an arrow. And because you've done lines and you've done parabolas, we have coached you arrows, 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 but not with a square root. There's only an arrow on this side. Why? Why isn't there an arrow here? Because none of these values are going to work. These are the values that are going to make the square root negative, so it can't continue on in that direction. These guys are okay because they're the positive values. There's never an arrow on this side. How are we doing so far? Here's a working backwards question. The exam loves these, the textbooks love these, because working backwards means you understand something better than if you're just working forward. We call it a higher order thinking skill. So it's one thing to know something, it's another thing to have to explain something, it's even more to have to work backwards from something. And sometimes the exam isn't going to use a cubic or a square root, it's going to use what I call a funky graph. It's just going to be some abstract graph that they give you because they want to know is can you apply this to all different kinds of functions. So I purposely didn't draw it in because I want you to draw it with me. We're going with red because this is like our final graph because we're working backwards. So I'm just going to give you some points. I'm totally making this up out of my head. I want you to put a point at -6, -2, -6, -2, and a point at -2, 3, -2, 3, and a point at 3, 3, 3, 3, and a point at 6, 4. Why those points? I made it up out of my head. Funky graph. It doesn't have a normal base shape. It's just something really cool. And we're going to join them with straight lines to make it even more funky. And I'm going to put an arrow on the right-hand side. Funky graph. So it's not a quadratic, it's not a cubic, it's not an absolute value, it's not a square root, it's nothing you've seen, it's just something funky that will be given to you in the question. Now the question says, given f of x minus 2 plus 3 below, draw f of x. So let's just label this so that later you know what this was. Has everybody here watched Jeopardy at some point in their life? Probably felt stupid. Yeah, me too. When they get those math questions, I'm like, yeah, they're like American history. I'm like, I don't know. Literature? This is like a Jeopardy question. This is giving you the answer. You're telling them what was the question. What did you start with? They've given you the final graph. They want you to go back to the original graph. So what we have to do is identify them and then pick them apart and do them backwards. So let's start with identifying. What was this -2? It's inside brackets. So it is horizontal. It's a translation. And it would have been, if this was the original question, it would have been 2 units to the right. How do we go backwards? We're going to end up doing 2 to the left because we're trying to work backwards from what the question gave us. The 3 that's on the outside of brackets all by itself. Outside means it is vertical translation. It would have been 3 units up. So to go backwards, we need to go 3 down. Now, if you really like the coordinate method with the table of values, is you could write out these coordinates if you want to. If you don't want to do that, we can count right off the graph. Now, you're not going to use red now because this is not actually the final graph. It's the beginning graph because we're working backwards. Pick some other kind of color. I don't care if it's pencil, if it's pen, just don't do it in red. So we're going to take point by point and we're going to count 2 to the left and 3 down. 1, 2, 1, 2, 3. 1, 2, 1, 2, 3. Bless you. 1, 2, 1, 2, 3. 1, 2, 1, 2, 3. And now we just match the graph that they gave us. The last one is in red lines, so our first one's, or in straight lines, so our first one's got to be in straight lines. It had an arrow on the right, so we're putting an arrow on the right. It didn't have an arrow on the left, so we're not putting an arrow on the left. And I'm just going to call this f of x just to show it was the very first graph, and now we're done the question. There's a working backwards. Look away. Look back. Did we take the blue, or whatever your color is, and to get the red, did we move it 2 to the right and 3 up? Would that land right on the red? Good to go.